Hi everybody. So in today's video, we're going to be going through the third set of AP review notes in preparation for the AP test. And in this video, we're going to address a variety of topics that are seemingly unrelated, but that often come up together in the same types of free response questions. So you might have a free response question where part A of the question is to estimate the derivative using a table. Part B would be to estimate the function using a tangent line. Part C would be to estimate an integral using a Riemann sum. These are all parts of questions that are often linked together by a prompt involving a table of values. So let's go ahead and just start by reviewing the different types of values that we can estimate in calculus. The first idea is that we can estimate the derivative of a function using a table of values. Now, obviously, the derivative is the slope at a single point. And so in order to calculate the derivative exactly, you would actually need to have a function take the derivative and plug in the number. When you don't have a function to use, for example, when you have a table of values, the best estimate for a derivative is to choose 2 points that are closest to the specified x value that you're trying to estimate, and then using those 2 points, do your regular old slope formula, which you may remember is y2 minus y1 over x2 minus x1. Or the way that we usually write it now, and we know function notation, is f of b minus f of a all over b minus a. Now, I will tell you the most common mistake that I see here in this type of question is that students reverse the values that are supposed to go on the top and put them on the bottom, and the values that are supposed to go on the bottom and put them on the top. And I think the reason that this happens is that oftentimes in a table, you look at the table like this, the x values are on the top. So what you need to remember is that the values in this fraction are actually the reciprocal of the values in the table. So this is usually the bottom row of the table, and this is usually the top row of the table. And I think students reverse those by accident because they're just copying the values out of the table instead of remembering where those values should go and that they need to be reversed from what they are in the table. So the second thing that we can estimate in calculus is we can estimate a function value. So we're estimating the value of a function, and we do that using a tangent line. Now, in order to make this happen, you're going to need to start by writing the equation of the tangent line. And to do that, we say you always need a point and a slope. As a reminder, to find your point, you take your x and you plug it into the original function. Now, sometimes this is given as an initial value in the problem. So sometimes in the directions, they will actually tell you the y value for that x value. Other times you may need to actually plug that x into an equation or find that value in a table somewhere. To get the slope, you plug the x into the derivative, or sometimes that is written as dy over dx, but you actually need to plug in your x value. And then you write the equation of your tangent line using point-slope form. So that would be y minus y1 equals m parentheses x minus x1. Now, after you have your tangent line, the next step is going to be to rearrange that equation to get y by itself, which means your new equation is going to look something like this: m parentheses x minus x1, and then since you're rearranging, you would add the y1 to the other side. And finally, you're going to plug in the x value that you're trying to estimate. So this x value and this x value are not the same x values. Your tangent line will probably be at a specific number that's nice to plug in, like the number 2, and you might be trying to estimate what happens when x is 2.1. So these are not the same x values, but you're using this x value to estimate this one. Now, in addition to estimating a function value using a tangent line, we are often asked to determine whether the estimate that we just calculated is an over or an underestimate. Now, in order to do that, you need to use the concavity of the function. And as a reminder, that means you're going to be looking at the second derivative of the function. So that might mean you actually have to find the second derivative and then plug in your number to determine the concavity. If you have a function that's concave up, then all of your tangent lines are going to be below, which means that you're going to have an underestimate. So whatever value you estimated for y here is going to be below the actual value that you would be able to calculate if you had a calculator or if you could plug it into the original function. Now, as a reminder, concave up means that the second derivative is greater than 0, is positive. Concave down means that the second derivative is less than 0. And when that happens, it's a different visual. We have a concave down like a frown, which means all of our tangent lines would be above. So all of our estimates would be over estimates. All of the values we're estimating would be too big compared to the actual value. The third thing we are often asked to estimate in calculus is the value of an integral using a Riemann sum. So here we're estimating an integral using a Riemann sum or a trapezoidal sum. Now, there are three types of Riemann sums. There's a right Riemann sum, left, and midpoint. And the difference between these three things is which endpoint of the individual intervals you use in order to determine the height of your rectangle. So in this picture, you'll notice for all of these rectangles, if we look at one single interval, the right side of that interval is what we use to determine the height of the rectangle. In this picture, you can see a left Riemann sum. The left side of the rectangle is what we use to determine the height of the rectangle. And for midpoint, it's the middle point of the rectangle that we use to determine the height of the rectangle. Now, for a trapezoidal sum, instead of having rectangles, we have shapes that are trapezoids. Now, when you organize your work here, it's really important that on the AP test, you always show your work. You want to show your setup and you want to show your work for performing these calculations. And the reason you want to do that is because oftentimes if you have a mistake in your actual calculations, by showing your work, you can get partial credit for that problem. We also taught you that there's a very specific way you want to organize your work here. So if we have 4 subintervals here, I would draw 4 little boxes. If it's a right Riemann sum, I would show the height of the rectangle by drawing a line on the right side only. Along the bottom here, we're going to list the x values that are the beginning and the end of each interval. And at the top here, we would list the y values that determine the height of that rectangle. And as a reminder, your area would be base times height. Now, similarly, for a left Riemann sum, if we had 4 subintervals, the only thing we would change is we would draw the height of those rectangles on the left side, and the area would still be base times height. For a midpoint Riemann sum, if we have 4 subintervals, we said you would draw your height kind of smack dab in the middle, and your area would still be base times height. The only formula that you need to know besides base times height is the area of a trapezoid. Now, we said for a problem like this, you would draw your 4 subintervals and you would show the heights on both sides because for a trapezoid, you need both sides of the interval. And in this problem, the area formula that you would use would be 1/2 times the height times base 1 plus base 2. Now, some people write that formula as height over 2 times base 1 plus base 2. It doesn't really matter. At the end of the day, it's the same formula. Now, once we've determined our estimate using a Riemann sum, we are often asked to determine whether that estimate is an over or an underestimate, just like we were asked to determine whether our tangent lines gave us over or under estimates for function values. Here, we're asked to determine whether our integrals are giving us over or under estimates when we use a Riemann sum. For left and right Riemann sum, whether you have an over or underestimate really depends on whether your function is increasing or decreasing. And this is information that you can usually find in the instructions to the question. So what you want to kind of imagine is drawing a picture. That's going to be the key here. For example, And I'm not going to do all of the different combos, but for example, if you have an increasing function and a left Riemann sum, so I would draw an increasing function and I would draw a left Riemann sum. And I can see, even if I only draw one rectangle instead of several, that this would be an underestimate. There's really no good way to memorize all these options other than just drawing a picture and visualizing what's happening. Now, that's what you're going to do for a left or a right Riemann sum. They're never going to ask you if your midpoint Riemann estimate is above or below an over or under estimate, because you can see that these rectangles are not always below or always above. There's a little bit above and a little bit below the curve, and so they're never going to ask you whether that's an over or under estimate. Instead, they might ask you for a trapezoidal sum, whether you have an over or under estimate, and this is going to depend on whether your function is concave up or concave down. So you're going to look at a different piece of information, which, as a reminder, means you want to look at the second derivative. So if you don't have the second derivative, you're going to want to find the second derivative, or it might be given in the instructions that the function is always concave up or always concave down. Again, I think sketching a picture here is really important. If we start with a function that's concave up and we draw a trapezoid, we can see that our trapezoid is too big. And if we start with a function that's concave down, and we draw a trapezoid, we can see that our trapezoid is too small. So I think it's really important to sketch a picture here, and I wouldn't try to necessarily memorize these answers, but I would definitely try to sketch a picture to figure it out. Now, the next topic that we're going to go over is how to interpret these results. So once you're asked to calculate or estimate these values, you're often asked to interpret these values in the context of the question. Remember, when we're interpreting, we always want to include a noun, the units that are appropriate for the answer, and the time, whether it's an interval or at a single moment in time in our answer. If we are interpreting a derivative, the noun that you want to use here is rate of change. So you always want to say that you're finding the rate of change of the quantity that you're measuring. For example, you might say it's the rate of change of the temperature, or the rate of change of the amount of compost left in the bin. The units here are always going to be calculated by dividing the given units, because remember, you're doing a derivative, which is a slope, and slope is always rise over run. So for example, appropriate units might be something like pounds per hour, or you can write that as a fraction, pounds per hour. If, for example, your problem already started with pounds per hour, then the appropriate units for the derivative would be pounds per hour per hour. So you're dividing again, and you would have like hours squared on the bottom. Now, a derivative is the slope at a single moment in time. So for your time here in your interpretation, you would say that t equals whatever x value you used to either estimate or calculate the derivative. If we are asked to interpret the meaning of the integral of a rate function, so anytime you have the integral of a rate function, so that could be, for example, the integral from a to b of r prime of t dt, or sometimes instead of calling it r prime, they just call it r of t, but in the instructions, they tell you that that's a rate function, so it's a rate. The noun you want to use here is the word amount, that the quantity being measured has changed. For example, it could be the amount of snow that has accumulated, or the change in the amount of snow. The units here are going to be the multiplication of the given units. For example, if you're starting with inches per hour and you multiply by hours, you're going to end up just with inches. And because this is an integral, it's happening over an interval of values. So you would say it's from t equals a to t equals b, because you're always going to have an interval of time, a beginning and an end for your integral. Now, all of these ideas often appear in the context of a table of values problem. So we're going to go through just a really, this is not an entire FRQ, but just a few examples that they might ask you to do with a table of values. It says here concert tickets went on sale at noon, which is t equals 0, and were sold out within 9 hours. The number of people waiting in line to purchase tickets at time t is modeled by a twice differentiable function L, for 0 is less than or equal to t is less than or equal to 9. Values of L of t at various times are shown in the table below. So for part A, it says use the data in the table to estimate L prime of 5.5, and then using correct units, interpret the meaning of your answer in the context of the question. It's really important here to read the directions carefully because there are two parts to this question. First, we need to estimate L prime of 5.5. Then, using correct units, we need to interpret the meaning of our answer. So let's see. Let's start with just the estimation. In order to calculate a derivative exactly, we would actually need a function. So because it says that we have to use this table, we're going to be coming up with an estimate. So what I'm going to do is find the location in the table where 5.5 would be located. Now I'm seeing that 5.5 would be in between the 4 and the 7. So I'm going to use these two ordered pairs to perform my slope operation, and I'm going to find the slope. So I would say L prime of 5.5 is approximately, and I'm using the approximately symbol because it does say that I'm estimating. And I'm going to put my change in y, which is 150 minus 126, divided by change in x, which is 7 minus 4. Now, if I have a calculator, this might be something that I type in, but I happen to know without typing it in that this is 24 over 3, which just gives me 8. So that's the first part of the question. The second part of the question is asking me to interpret the meaning of our answer in the context of the question. So what we're going to say is that L prime of 5.5 gives the rate of change. Remember, we need a noun first. So we're going to say the rate of change, because we found a derivative, of the thing that we were measuring. And here we were measuring the number of people waiting in line. Now, after we have our noun, we want to go ahead and give our units. So we would say measured in and now we're going to divide the units we were given, people per hour. And then we need to state our time. So we would say at, and then our specific x value. So t equals 5.5 hours. So we've got our noun, we've got our units, and we've got our time. Now, part B of this question says, using a trapezoidal sum with 3 subintervals, estimate the integral from 0 to 4 of L of t dt. So what we're going to do here is really only one thing, estimate this integral, but they tell us specifically to use a trapezoidal sum. Now what this means is that at the end of the problem, I want to be able to say that the integral from 0 to 4 of L of t dt is approximately something. Now I'm going to do the work to do those computations below here. I'm not going to put it equal to here. I'm not going to put it as part of this answer. I'm going to kind of show my work in a separate place. So the work is going to be this. If we're going to use a trapezoidal sum with 3 subintervals, I'm going to start by drawing 3 subintervals. Now it says that I should go from 0 to 4, so I'm only looking at this part of the table right here. To make 3 subintervals, I would go from 0 to 1, 1 to 3, and 3 to 4. So I would list 0, 1, 1, 3, 3, 4. Now I'm using trapezoids, so I need both sides of each interval. Those are the bases of my trapezoid. And I would list my y values here: 120, 156, 156, 176, 176, 126. Now, in order to perform this computation, I would be doing 1/2 times the height, which is 1, times base 1, which is 120 plus 156, plus base 2. Plus, I would do 1/2 times the height. The next height would be 2, from 1 to 3 is 2, times 156 plus 176. Plus, I would do 1/2 times the next height is 1, and then 176 plus 126. You'll notice I'm showing my setup of my work here. Now, because we could possibly have a calculator, on this year's AP test, we will definitely have a calculator because it's at home. I'm just going to go ahead and type this in. And when I do that, I should get 621 as my final estimate here. All right, now we're going to kind of change gears a little bit, and we're going to look at one FRQ topic that we see frequently in tables of values problems, but sometimes we also see as an entirely separate FRQ. So the thing about related rates, which is what we're going to review next, is that sometimes related rates is its own FRQ question. And sometimes related rates and these types of problems are built in as one part of a bigger FRQ. So this might be part C. What I'd like to do is start by talking about how do we recognize related rates. So what should we look for to recognize that we're dealing with a related rates problem? Then we will talk about a strategy for solving. So what steps can you work through mentally so that you can try to approach this problem efficiently and get the right answer? And last but not least, we're going to go ahead and do an example problem. So the first thing I'd like to talk about is recognizing related rates. Whenever you see multiple variables and multiple rates mentioned, it is probably a related rates question, because a related rates question is just asking us about rates that are related to each other. So if there's lots of rates that are all changing with respect to time, then we're probably looking at a related rates question. Now, the question will often either ask for the rate of change with respect to time or give you several separate rates of change with respect to time. An example would be like this. Ship A is traveling due west towards Lighthouse Rock at a speed of 15 kilometers per hour. Ship B is traveling due north away from Lighthouse Rock at a speed of 10 kilometers per hour. So these are rates with respect to time. And then it says find the rate in kilometers per hour. So find a rate that is with respect to time per hour. As soon as I see that, it sort of should be a buzzer in my head saying this is a related rates question. Now, my strategy for solving is going to involve these steps. Number 1, draw a picture if one is not given to you. In a lot of cases, these pictures are already provided. For example, in this real-life FRQ question from a previous AP test, they actually gave us a picture with a bunch of variables so we could visualize it. If there's not one, you might want to draw your own. Then you're going to list what you know. When you're reading these questions, there are going to be lots of words, and you don't want to have to keep going back to the words and kind of filtering them every time. So you want to kind of list using symbols in a concise way what you actually know. Finally, you want to find a formula to relate the quantities in the picture. So that is usually going to be a pretty obvious mathematical formula like Pythagorean theorem, or a trigonometric formula like sine equals opposite over hypotenuse, or it might even be a volume or an area formula. Last but not least, you're going to take the derivative and make sure to use implicit differentiation. Since everything here is changing with respect to time, everything gets its own little derivative attached to it. Finally, you're going to plug in your values and solve. So let's go through a practice problem. In this example, we were given a picture already. Let's list what we know. From the directions here, it tells me that ship A is traveling due west towards Lighthouse Rock at a speed of 15 kilometers per hour. Now, if I look, ship A is here. They've already labeled that X is the distance between this ship and the lighthouse, and ship A is going back towards the lighthouse. How fast that's happening, I'm going to call dx over dt. Now, dx over dt is going to be 15 kilometers per hour. But since my ship is going back towards the lighthouse, I'm going to make this negative because the length of this side of the triangle is getting smaller. It's going back towards the lighthouse. Ship B is traveling due north away from the lighthouse at 10 kilometers per hour. So ship B is going north, which means dy dt would be 10 kilometers per hour. And I'm going to leave this positive because that length of that side of the triangle is getting longer. Finally, it says, find the rate of change in kilometers per hour of the distance between the two ships. Now, the distance between the two ships would be the hypotenuse of this triangle, and it doesn't have a label yet. So I'm going to go ahead and put one in, which is d. dd over dt, the rate of change, is what I'm trying to find. It also tells me that at this moment in time, x is 4 kilometers, y is 3 kilometers, and those two values should sort of be triggering in your mind that this is a 3, 4, 5 right triangle. So if we need it, we could figure out that d would be 5 kilometers. All right, now using that information, I'm going to try to figure out a formula to relate these quantities. As soon as I see a triangle where I have all three sides, I'm going to think Pythagorean theorem. So the Pythagorean theorem here would be x squared plus y squared equals d squared. Then I'm going to take the derivative, which means I'm going to have 2x and then times dx over dt. This little dx over dt is what I mean when I say use implicit differentiation, because we're showing that x is changing with respect to time. Just like whenever you take the derivative of a y, which is the dependent variable, we would always write dy over dx. In this case, since x is changing on its own, we would write dx over dt. Plus, and then I would take the derivative of y. So 2y times dy over dt equals, and then I would take the derivative, which is 2d times dd over dt. Now from here, I'm just going to plug in my numbers. So I would have 2 times 4 times negative 15 plus 2 times 3 times 10 equals 2 times 5 times dd over dt. And you know you've done something right when the only thing left in your equation is the thing you were trying to find in the first place. Now again, I could use my calculator or I could do the arithmetic by hand, but this side of the equation simplifies to negative 60 equals 2 times 5 is 10 times dd over dt, which means the rate of change of the distance between the two ships would be negative 6 kilometers per hour. And using units here in your answer is going to be really important. So make sure to include units in your answer. Now you'll notice that in this picture, there was also a theta here. And you might be wondering, well, what the heck is that for? The reality is that this was one part of a multiple part FRQ question. And the next part of the question asked for the rate of change of theta. So to set that up, I would probably use a tangent function. And I would say tangent of theta equals y over x, opposite over adjacent. And then I would do the same process, but I would be starting with an equation that involved a trigonometric function instead. So don't let that theta freak you out. That was just a part that was relevant for a different portion of this question. All right, now the last part of today's video is actually going to be by request. One thing that several students have asked for is more clarification on the intermediate value theorem and the mean value theorem. In a previous video, we already went through the conditions that must be met, and we already went through the conclusions and kind of steps for explaining your work. What I'd like to focus on here is how do we recognize these theorems? So if I'm reading a question, how do I recognize that I'm supposed to be using the intermediate intermediate value theorem, and how do I recognize that I'm supposed to be using the mean value theorem? Now, in both of these examples, we're given data where we have a velocity function, but it really comes down to the question that we're asked. Here's how you recognize the difference between these two problems. In this problem, it says, does the data in the table support the conclusion that train A's velocity is negative 100 over this specific time interval? What you're going to notice here is that we are asked to determine whether this is true or false. Does the data support this conclusion that the velocity, which is what we were given, is equal to a specific number? If we are asked to guarantee a specific y value that is between values we already have, so velocity values are what we have, do we have this number in between the ones that we have? We're also going to be given an interval. So every theorem question is always going to give you a specific interval, so between 5 and 8. Now in this question, which I'm not going to work through, but I would suggest maybe thinking through it on your own, it says look between these two numbers, so specifically focus between 5 and 8. Can you promise me that the number negative 100 would fall between those two numbers? Well, the answer is yes, because 40 is bigger than negative 100 and negative 120 is smaller. So in order to get from a positive 40 to a negative 120, you would have to pass through the negative 100, which is what the intermediate value theorem says. And that's how I know I can use the intermediate value theorem to justify this answer. Now for the mean value theorem, and again, we're still given a velocity function, it says justify why there must be at least one time for, and again, we're given a specific interval, at which v prime equals 0. Now you'll notice here, this does not say v of t anymore. It doesn't say velocity. It says the derivative of velocity, the derivative of what we have. Here we are being asked to guarantee a derivative value. And that's the difference. If we're being asked to guarantee a derivative, we use mean value theorem. If we're being asked to guarantee a y value, we're using intermediate value theorem. In both of these cases, we're going to be given a specific interval. Now, in this problem, we're looking specifically between 0.3 and 2.8, which is this interval right here. Now, a derivative is a slope. So what I would do here is I would find the regular old slope. So I would do change in y, which is 55 minus 55, over change in x, which is 2.8 minus 0.3. And since 55 minus 55 is 0, this is going to give me 0. Since my average slope is 0, the mean value theorem says that my derivative must be 0 at some value. Now, this is an example problem from a previous year's AP test. This is actually from 2007, where in this year's AP test, they actually decided to build all the theorem questions into one free response question. So part A was a theorem question and part B was a different theorem. And so what we're going to do here is kind of work through this question to show you how you might identify that you should use the theorem and then justify your answer correctly. It says here functions f and g are differentiable and g is strictly increasing. The table gives the values of the functions and their first derivatives at selected values of x. The function h is given by h of x equals f of g of x minus 6. So we're given a table that has f of x values, f prime of x, g of x, g prime of x. Part A says explain why there must be a value r between 1 and 3. So right away, this should be jumping out at you because we're given an interval and such that h of r equals negative 5. Now, h of r means a y value, a function value. So since we are asked to guarantee a y value, we're going to be using the intermediate value theorem in this question. Here's how we would do that. In order to determine that we can actually guarantee this, we need to find h of 1, which is the first x here, and we need to find h of 3, which is the second x here. Unlike the previous problem where we actually already had velocity values in our table, here we don't have h values in our table. But since h of x is related to f and g, we can find those values using what we have in our table. So h of 1 means plug in the number 1, which means I would have f of g of 1 minus 6. Now, g of 1 I can get from this column of the table, which would be 2. So I would have f of 2 minus 6. F I can get from this column of table, and f of 2 is 9. So I would have 9 minus 6, which is 3. H of 3, I would follow a similar process. So I would have f of g of 3 minus 6. G of 3 would be 4. So I would have f of 4 minus 6, and f of 4 is negative 1, and negative 1 minus 6 is negative 7. Can I guarantee that negative 5 exists? Well, yeah, because negative 5 is between these two values. So that's ultimately what I need to say as part of stating my conclusion here. So here's what I would state for my conclusion. I would say there must be a value R for 1 is less than R is less than 3, such that h of R equals negative 5. So explain why there must be these things. There must be those things because of IVT. And then I would say it met those conditions that were necessary for the IVT. So I would say colon h of x is continuous and h of 3 is less than negative 5, which is less than h of 1. Now, by contrast, if I look at the next question, it says explain why there must be a value for the same interval where h prime of c equals negative 5. The big difference here is that we are being asked to guarantee a slope or a derivative, which means we're going to use the mean value theorem instead of the intermediate value theorem. So in order to do this, we need to actually find the slope over this interval between 1 and 3. So I would do h of 3 minus h of 1 over 3 minus 1. Now we're lucky that we already found those values. So we would have negative 7 minus 3 over 2, which is negative 5. Since my average rate of change is equal to negative 5, I can guarantee that my instantaneous rate of change must be negative 5 by the mean value theorem. So I would say since h of x is continuous and differentiable, which are the conditions of the mean value theorem, and h of 3 minus h of 1 over 3 minus 1 equals negative 5, and since my average rate of change is negative 5, there must be a value c for 1 is less than c is less than 3, such that h prime of c equals negative 5 by the mean value theorem. So since I've met these conditions, I can now state this conclusion, which I just copied from the question, using this theorem. All right, I hope that this is helpful, and thank you guys all so much for watching. I hope you have a wonderful day, and I will talk to you soon.